I want to spend some time this evening talking about topographic mapping and the processes we use to go from field data to contours. This will be useful for you to understand how we do it manually so that you can troubleshoot when things go wrong when we do it digitally. For clarity's sake, I'm going to use a CAD file here, but step through some of the manual processes. And you're going to have to use your imagination a little bit, but I'm going to do my best to give you a good visual overview of what happens. What I'm showing on the screen right here is a series of elevation shots taken on a small site on the Parkland campus. If I zoom in here a little bit, you'll see that everything's got a point number associated with it. For instance, point 115, 114, and these data were collected by simply walking a grid, a serpentine grid, as you see my mouse moving back and forth through here, a serpentine grid with a simple GPS rover and collecting horizontal positions and elevations. Well, where do we get those positions and elevations? I have a simple Excel file here that gives point number, northing, easting, and elevation. And then over here in column E, you can see ground shot showing up, or a code for a ground shot. So all these are ground shots. The fourth column over shows an elevation. The northing and easting are used, of course, to locate the point in this plan view, and then the elevation establishes its position in the Z direction. The point numbers that are on this list correspond to the point numbers that you see up here on the screen. For instance, point 115 has an elevation there of 776. We'll call it 776.2. Well, if I go looking in here, there's point 115. Now, we'll see elevation show up on this in a little while. What we do first is develop what we call a triangulated irregular network. My software has already done that for me. I'm going to turn that on. And that triangulated irregular network looks like this. We're simply drawing lines between our measured points, and those lines are drawn in 3D space in this case. Let me show you that. If I can, I'm going to rotate this thing up so that you can see a little bit of this shape. Now, this is a fairly flat site, but I think you can see as I move it here that running this way through the site, there appears to be a drainage swale. And that is indeed the case. This is not mountainous terrain like you might find in other parts of the state. This is central Illinois prairie. Now, if you want to see indeed that does have some elevation change in it, if I take an edge view of it, you can see that yes, there is some elevation change. If I go back to a top view, we have what we had before. I want to illustrate for you how we go about using this triangulated irregular network. Whether we do it in 3D digitally like this shows, or we do it in 2 dimensions on a piece of paper, the process is the same. In the computer-aided drafting world, it does everything mathematically based on the 3D coordinates of every little node you see here. One thing I want you to notice about this triangulated irregular network is the fact that none of the triangle sides cross each other. That is, every triangle has as its vertex one of our shot locations. No triangle side crosses any other triangle side. You could think of this as every triangle forms a plane. And these planes are all tilted relative to each other, but they join each other at the edges. Well, these planes then hopefully describe the shape of the ground. Thus, our shot locations should coincide with break lines. In this case, The break lines are not very clearly defined because the site is fairly gently rolling. To illustrate where we're going with this, let me show you what we're going to have. We're simply going to have contours that show our relief here, and you may already know that when we have contours that form V's in a successive set of parallel V's like we have in this case, if you look carefully at the numbers, here's 778, 777, 776, 775, you can tell that we're going downhill. And when you're going downhill and these V's point uphill, well, that indicates that you are in some kind of waterway. And indeed we have a swale that allows natural surface runoff to collect and run from northeast to southwest in this site. Let's spend a little time talking about how we get from this triangulated irregular network to the contours that you see here. What I've shown here in this area is at the shot locations, I have elevations, and I've rounded them all to the nearest tenth of a foot. Now I want you to consider that from this point here where we have 776.2, which is my point 115, all the way up to this point, which is point 114 at 777.4, well, I have a total of 1.2 feet of elevation difference. That is 777.4 minus 776.2 gives me a difference of 1.2 feet. So I need to find where between those two I will have a contour line crossing through. If I am trying to draw contours on a 1 foot contour, then I know between these 2 points, 776.2 and 777.4, the 777 contour will cross through here. Its location is going to be some fraction of the distance from one end to the other. So what I'm going to do is consider dividing this distance, this horizontal distance, up into 12 parts corresponding to 12 tenths or 1.2 feet. Rather than put 12 marks there, I'm going to go 6 marks. In fact, 6 marks scattered between here and here or 6 increments, I should say. It requires that I place 7 marks. I'm going to draw some marks here. Let me tell you what they indicate. If this elevation is 776.2, then the elevation at this x would represent 776.4. This would be 776.6 here, and 776.8. And at this x, I would have 777, 777.2, and 777.4. What I'm assuming is a uniform slope along this line from 776.2 up to 777.4. Well, if that's the case, then I have 1, 2, 3, 4, 5, 6 increments here. 777.0 is 4/6 of the way, or in this case 8/12 of the way, from 776.2 to 777.4. Because this is a uniform slope, I'm trying to place a point that puts me at the right spot. I'm going to delete these extra ones so that this one just represents 777.7. Well, I need to just do this in a couple more places as we go here, because I need to do it on every one of these lines on my triangulated irregular network. So bear with me here and we'll get this cranked through. Looks like I have 776.9 and 777.4. That's a difference of 5/10 of a foot. So I need to place, in my case, a total of 6 spots. And I can see that this one would be at 777.0, 1, 2, 3, and 4. So I'm going to take that one out, that one, and that one. Then, between this one and this one, I should have two contours falling, correct? 776 somewhere in here and 777 somewhere up there. So that's a total of, let's see, that's 775.6, so 7.4 minus 5.6 gives me a total of 1.8. All right, so if that's 1.8, and if I need to go, well, I'm starting on an even, ending on an even, I'm going to do that with 9 increments, so I need to place 10 spots. So this is 775.6.8. This would be 776.2, 0.4, 0.6, 0.8, 777.2, and then 0.4. Let's keep going. 775.6 to 776.9, so that's 6.9 minus 5.6. That gives me 1.3. So that's 13 increments of 1/10. I'm going to go ahead and do it as 14. Okay. And I know that between here and there, I'm just going to have the 776 contour, correct? Okay, so that was 775.6, 7, 8, 9, and then this is 1, 2, 3, 4, 5, 6, 7, 8, and 9. So my 776 contour is going to cross through right about here. And you can see, well, this kind of makes sense. 777 is going to cross through like so. If I keep going here, bear with me, 2 to 9 is 7. Think about this. 776.9 to 776.2, there is no whole contour that's going to cross between those. It's not going to be 776, and it's not going to be 777. So I won't have a contour crossing through here. But I will between these two. See, this one's 775. There's 775, and then here is 776.2. So let's take a look at that. 6.2 minus 5.6, that's 6 increments, so I'm going to place 7 units. And that means this is 5.6, 5.7, 0.8, 0.9, 6.0, 6.1, 6.2. Okay, let's keep going. Same kind of thing here, right? Same elevation difference. Zooming in, cleaning it up. Looks like this. 0.7, 0.8, 0.9. There's 0.0, 0.1, 0.2. Over here, look carefully. 6.2 to 8.2. That's a total of 2 feet. 20 increments. I'm going to divide it up into 10. Actually, if it's 10 increments, I need 11 points. 0.2, 0.4, 0.6, 0.8. So this would be 0.7, 0.2, 4, 6, 8, 0.8, 8.2. Likewise, look here, 5.6, I'm going to have 6, 7, and 8 fall on here, so there's 8.2 minus 5.6 gives a total of 2.6. So that's 13, I'll divide that into 13 increments. It's 2.6 feet or 26 tenths. Since I'm starting and ending on evens, I'll make it 13 increments for 14 points. As we finish this up, you're going to see a pretty interesting pattern. 0.6, 0.8, this would be 776, 2, 4, 6, 8, 8 tenths. This would be 777. This would be 777.2, 0.4, 0.6, 0.8, 778, 778.2. Between these two, I should have what? The 776 and the 777 contour crossing through in this vicinity. So I have 7.9 minus 5.6. That gives me 2.3. So that's 23 1/10 increments, and I need 24 points to place that. This will look a little messy for a little bit. Okay, that was 775.6, 0.7, 0.8, 0.9, and this is 776.1, 2, 3, 4, 5, 6, 7, 8, 9. This will be now be 777.1, 2, 2, 3, 4, 5, 6, 7, 8, and 9. So at this point we have 776, 777. Notice on this line between 775.6 and 775.2, there will be no contour crossing through there, will there? Here I'll have the 776 between the two. So let's get that one in the right place. I know this is probably like watching paint dry, but I want you to see the pattern so you can understand clearly how you can do simple contour plotting by hand. Let's see, I'm going to do a total of 6. 2.4, 0.6, 0.8, 1 or 6, and 0. Okay, a couple more lines. Looks like I won't have anything on this line. I will have on this line and this line. So 2 more lines, and then we start to do something different. On this line, 7.9 minus 5.2 gives me a total of 2.7. And I'm going to make 28. The reason I chose 28 here is I know that it is 2.8 feet vertically from here to here, because one end of the line has an elevation ending in an odd number. I want to go ahead and divide that into 27 increments. I've placed 28 points to do that. Those two of those are at the end points. And then I'm going to take out the ones that don't correspond to a whole foot. There's 0.2, 0.3, 4, 5, 6, 7, 8, 9. And this would be at 776. Then 776.1, 2, 3, 4, 5, 6, 7, 8, 9. And then that's 777, right? 0.1, 2, 3, 4, 5, 6, 7, 8, and 9. Okay. One more line and we've got it. Okay, 777.4 minus 5.2 is 2.2 feet. Because both of them end in an even value, I'm going to go ahead and consider that's 11 increments of 0.2 feet per increment. Place 11 increments, I need 12 spots. And here we go. This is 777.4, 0.2, this would be 777, 0.8, 0.6, 0.4, 0.2, this would be 776, and then 775.8, 0.6, 0.4, and then 0.2. I missed one. Between these two, here's 777.9 and 778.2, so I think you can understand 2/3 of the way from here to here, 778 is going to fall in there, isn't it? This would be 778. And if you think about this carefully, you will see that I have some points that are all a common elevation. I know I have some that are 776, and I'm going to label these things. These would all be 776, and that one would be, and this one, and this one, and this one, and this one. Now, 777 shows up in a couple of places. Here, and here, and here. We also had a 777 showing up there, 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 and there. We had 778 over here on the edge. That showed up here, here, and here. I think you can see I'm going to have a contour running up through here connecting all these 777s, aren't I? And I'm going to have a contour that connects all these 777s. And there's a 777 over here, and a 778. I have the advantage here of allowing my software to do it for me. But let's see how closely everything comes to hitting. Oh, look at that. Even though my software has done it for me, the process by which I have, I guess you could say, reverse engineered this, hits pretty darn well, doesn't it? In fact, you need to understand my elevations as I've shown here are shown to the nearest tenth, although they were computed based on elevations shown to the nearest hundredth. So yeah, there's going to be a little bit of a difference between my X's and the contours as shown here. So what you see here, these contours are drawn dot to dot. They're shown as straight lines. But I think you have probably noticed that on a lot of contour maps, our contours tend to be somewhat smoothed out. And computationally, we can do that. Does the smoothing get us farther from reality? Well, not necessarily. Let's take a look at what we get if we apply a basic smoothing technique. If I reload this, notice what happens. You can see here that at this 776 vertex, now my contour doesn't exactly hit the shot. But do you suppose this more closely resembles what we see on the ground? Probably so. Look how I've got some directional change back here. Let me go back so you can see what that nose smoothing looks like. See, I've got sharp little vertices. I go with some smoothing, and it starts to make it look a little better. Well, if I go with a more aggressive smoothing technique, notice that it starts to slick it up quite a bit more. And you can see a smoothing routine here relative to absolutely no smoothing. The smoothed contours are probably a better representation of the natural surface. One of the implications of this is our contours are definitely an approximation. It is a model, and it is a simplification of what we've seen in the field. Moral of the story here. When you are plotting contours, the first thing to do is to start with your plotted points, and you're going to connect the dots with triangles. Remember, your triangles, the sides must not intersect. For instance, you know that you could draw them different ways. I have drawn triangles going this way. But just as easily, those lines could have been drawn a different direction. I could draw a line from here to there, and to there, and to there. And the question becomes, do I draw a triangle this way, or do I draw a triangle from there to there? I don't want you to worry too much about that. Over time, experience will tell you, but over time you'll realize that you're not going to be doing it by hand, and your software will be deciding for you. When in doubt, jump in. And a little trial and error and a little bit of what-if analysis can help you see the relative advantages of choosing one way over another. In summary, then, you're going to go first from plotted points to a triangulated irregular network, as you see here, to contours, as you see here. With those contours, then, your triangulated irregular network then becomes secondary. And now, as we see our model, you can start to see how the contours fit that ground shape. If I look at the side, you'll definitely see that all those contours form flat planes. And the dashed line that you see here is the flow line of our swale. as you use topographic surveys in the design realm in your careers, you'll be able to fall back on this understanding of how contour maps are generated, and thus be able to do some good troubleshooting and work closely with your field crews to ensure that the detail that you request is the detail that they provide. Thanks for your attention. I'll be talking to you again soon.